Welcome to Math with Professor V. In this video, I will be working through and solving the most recent exam I gave my Calculus 3 class, Multivariable Calculus. It covers partial derivatives, local and absolute extrema, or relative or global, depending on whatever your textbook calls it, Lagrange multipliers, directional derivatives, and more. I'm just going to work through and solve the problems. And if you need a more in-depth video lecture on any of the topics, then you just check out the description of the video and I've got them all linked there for you. Okay, here we go. First, we're starting off with limits. Evaluate each limit or show that it does not exist. I have a stellar video going over multivariable limits. If this is something you struggle with, check it out. Okay, so this first one, I'm going to test two different paths because I suspect it does not exist. Remember, if you're checking paths, you can never use that approach to prove a limit exists. I go over this in that video. So I'm going to first go along the path x equals 0. So then I have the limit as 0y approaches 0, 0. I'm going to substitute in 0 for x into my expression here. So I'll have y squared times sine squared of 0, over 0 to the 4th plus y to the 4th. This becomes the limit as 0y approaches 0, 0. Simplify first. Don't try to take the limit. I have sine squared of 0, that's 0, times anything is going to be 0, over, I have 0 to the 4th plus y to the 4th, that's just y to the 4th. Okay, again, simplify. Don't try to take the limit. 0 over y to the 4th is just going to be 0, which is a constant, and the limit of a constant is itself. Okay, so that's the limit along x equals 0. Now I'm trying to get a different number, a different value. Therefore, I can show that the limit doesn't exist. So let's try along y equals x. If I try along y equals 0, I just get the same result. So that'll get me nowhere. So now we have the limit as xx approaches 0, 0 of x squared sine squared x over x to the 4th plus x to the 4th. Good. So this is 2x to the 4th, which can cancel out two of the x's that are in the numerator. So then now I have the limit as xx approaches 0, 0 of sine squared x over 2x squared. So then you can rewrite this. This is the limit as xx approaches 0, 0. Hopefully you remember from Calc 1 that the limit of sine x over x is 1 as x approaches 0. So I basically have sine x over x squared, since I've got two of them there. Yep, two of them there. Beautiful. And then the 2, I just made it a cute little 1/2, so it's not threatening us. So this goes to 1. 1 squared is still 1 times 1/2. This limit is 1/2. So since different paths yield different limits, then we can say, like, these are not equal, clearly. Therefore, the limit as xy approaches 0, 0 of y squared sine squared x over x to the 4th plus y to the 4th does not exist. And I think some of them showed that the limit was dependent upon m. They went on a general linear path. I can't remember. So there was a couple different ways to show that it didn't exist. Okay? Good. So remember, the big thing is when you're testing paths, the only purpose is to show that the limit doesn't exist. There's infinitely many paths, so there's no way for you to test them all and show that they're all equal. Therefore, the limit does equal whatever. So how do you show a limit exists? One of the options is direct substitution. And if direct substitution doesn't work, then sometimes algebraic manipulation will fix things. So notice here, if I try to sub in 0, 0 for x and y, I get an indeterminate form, 0 over 0. But this radical is giving me hope. I'm like, maybe multiplying by the conjugate will allow me to play around with some things and fix it so I don't have an indeterminate form. So I'm going to multiply by the square root of x squared plus y squared plus 1 plus 1. And then now the denominator is going to be a difference of squares, right? So I'm just going to have x squared plus y squared plus 1 minus 1. I have this product minus that product. I will not multiply out my numerator because I know I'm going to want to cancel. So why multiply it out? I'm just going to have to refactor it in order to cancel. I don't want to do that. That sounds like more work. So those cancel. See, now I just have x squared plus y squared. Be gone. Be gone. Beautiful. So glad we didn't multiply out that numerator, aren't you? I'm always looking out for you guys. Okay, xy goes to 0, 0. And then we have square root x squared plus y squared plus 1 plus 1. So then now can we just use direct substitution? You bet. That's square root of 1 plus 1, 1. Oh, 2. Holy smokes. You guys, I've been sick the past few days. At first I was thinking I just lost my voice, then it spiraled out of control. So here we go. Okay, limit xyz goes to 0, 0, 0. I saw a bunch of people test along different paths and show that they had different values, so the limit didn't exist. It was clever too. Some of them I was like, ooh, it was a fun problem to grade. I think the cleanest thing though, if you just want to test along a general linear path that goes obviously to the origin, test along the line x equals at, y equals bt, and z equals ct. So it has direction vector v with components a, b, c. So then we can write this as the limit, t goes to 0, and then subbing everything in, this is going to be abt squared plus bct cubed plus act cubed over a squared t squared plus b squared t squared plus c to the fourth t to the fourth. Then you can just cancel out t squared from everybody. How thrilling. And we'll have ab plus bct plus act over a squared plus b squared plus c to the fourth t squared. So then now we'll take the limit as t goes to 0. Any term involving t would also go to 0. And I'm left with, yes, ab over a squared plus b squared. Now, since this limit, the value depends on the direction vector v, different paths will have different limits, right? Therefore, the limit doesn't exist. The limit of what? Let me tell you. The limit as xyz approaches 0, 0, 0 of xy plus yz squared plus xz squared over x squared plus y squared plus z to the fourth. That function's limit doesn't exist. Okay, very good. Last one. Limit as xy goes to 0, 0 of e to the negative x squared minus y squared minus 1 over x squared plus y squared. So for this guy, few options. I'm going to opt to go polar. The x squared plus y squared is just screaming at me. So remember, when you go polar, it only works if you're going to the origin. And so we're going to take the limit as r approaches 0 from the right. And the whole point of it is normally, in polar coordinates, we have r and theta. But if we're going to the origin and r is approaching 0, it's independent of theta. It will still get to the origin. So that's why we can reduce the number of variables in this limit. It's so fabulous. So then we have e to the negative r squared minus 1 over r squared. Okay, if you try direct substitution now, you still have an indeterminate form. Do you notice? It's 0 over 0. Yes, but we only have one variable in the limit. So we can use L'Hopital's rule. So we have the limit as r approaches 0 from the right. Derivative of e to the negative r squared would be e to the negative r squared times negative 2r. Minus 1's derivative is 0. Some of them mess that up. Derivative of r squared is 2r. So then the 2r's cancel, and then we should be good to go to just evaluate the limit directly. Limit, r goes to 0 from the right, negative e to the negative r squared, so that's negative e to the 0, which is negative 1. Voila. This was actually a pretty strong section for most people, so that was exciting. Okay, question 2. Find the linearization L of xy of f of xy equals 2 arctan of xy at 1, 1. Finding the linearization is the same thing as finding the equation of the tangent plane, but I'll just write out the formula. So L of xy equals partial with respect to x times x minus a plus partial with respect to y times y minus b plus f of ab. So I need partial with respect to x and y. So derivative of 2 arctan something would be 2 over 1 plus the something squared. And then we have to do the chain rule. So if I'm taking the derivative with respect to x, I'm holding y constant, which is basically telling me I'm going to multiply by y when I do the chain rule. So now I have 2y over 1 plus xy squared. And then if I evaluate this at 1, 1, then this will be 2 over 1 plus 1 squared. So that's 1. Okay, cute. Same thing, partial with respect to y would be 2x. So the chain rule just swaps out the x for the y over 1 plus x plus y squared, xy squared. And then evaluating this at 1, 1, it also turns out to be 1. Perfect. So the only other thing I need is the function at 1, 1. This was embarrassing for some people. 2 arctan of 1 times 1. That's just 2 times arctan of 1, 2 times pi over 4, which is pi over 2. Yeah. Okay, let's put it all together. So L of xy equals 1 times x minus 1 plus 1 times y minus 1 plus pi over 2. And then call in the cleanup crew. We'll write this as L of xy equals x plus y minus 2 plus pi over 2. Okay, beautiful. Very straightforward little problem. Yes, indeedy. Okay, evaluate del z del v at uv equals 2, 3 for the function z equals xy squared minus ln of x equals e to the u plus v, and y equals uv. You must also include an appropriate chain rule formula as part of your answer. So I'll draw the tree diagram. That was optional, but sometimes it helps with the chain rule formula. So z is a function of x and y are each functions of u and v. So if I want del z del v, find all the v's, and then start at the top, trace your path down to each of those branches. So that means del z del v is going to be del z del x times del x del v plus del z del y times del y del v. Those should all be partial derivatives. Okay, now let's see here. Del z del x is y squared minus 1 over x times del x del v is e to the u plus v plus del z del y is 2xy, and then del y del v is u. Okay, good. Now, I don't have what x and y are. They gave me u and v, so I have to go fetch that info, not a problem. So x is going to be e to the 2 plus 3, so e to the 5th, and then y is u times v, which is 6. So then back to the problem at hand. This is going to be 36 minus 1 over e to the 5th times e to the 5th plus 2xy would be 12 e to the 5th times u, which is 2. Then clean up. This distributes just gorgeously. 36 e to the 5th minus 1 plus 24 e to the 5th. And you're left with 60 e to the 5th minus 1. Bravo. Okay, moving on. Suppose that over a certain region of space, the electrical B is given by, I think I forgot the word potential. Oh well. Is given by V of xyz equals 5x squared minus 3xy plus xyz. Find that, yeah, it should be electrical potential. My bad. That's not a problem. Don't worry about it. Okay, find the rate of change of the potential at the point P of 3, 4, 5 in the direction of the vector V. So what we need here is the directional derivative, okay? So in order to compute the directional derivative of v at p, what I need to do is find the gradient of v at 3, 4, 5, and then dot it with u. So u has to be in the direction of v, but it needs to be a unit vector. And v's magnitude right now is, that's right, rad 3. So my vector u is 1 over rad 3 times 1, 1, negative 1. Now let's go ahead, let's get the gradient of v. The gradient of v is going to be 10x minus 3y plus yz, negative 3x plus xz, and xy. So if I evaluate the gradient at the point 3, 4, 5, I get 38, 6, 12. No, you can't scale this down. When you're asked to find a directional derivative that represents a quantity, right? That's a scalar. You're not giving an equation, so you can't scale it down. So don't divide by 2. Some people made that boo-boo. So this is going to be 38, 6, 12. Dot that with 1 over rad 3 times 1, 1, negative 1. Don't distribute the 1 over rad 3. Leave it outside. Have it mind its own business. This is 38 plus 6 minus 12, and you get 32 over rad 3. I don't need them to rationalize denominators. Nobody cares. Oh wow, what was that? Straighten up. There we go. Okay, in which direction does v change most rapidly at p? In the direction of the gradient, okay? So you could say 38, 6, 12. That's the direction of the gradient. Or if you want to scale it down, that's fine, since they were only asking for a direction. I say do less, right? Like, I don't know, it's dangerous when you take a test. Either one's fine for this problem. What's not fine is right here. What is the maximum rate of change at p? That means they want the magnitude of the gradient of v at p. And if you scaled it down, make sure when you go back and give this magnitude, you give it of the one that was not scaled down. That's why this is kind of a dangerous moment. So some people had a oops moment there. And this did need to be simplified. So it did. Yes, it did. 2 rad 406. Okay, they had a calculator. So no problem for them. Okay, moving on. Find equations of the tangent plane and the normal line to the surface at the given point. So all of this hinges on, that's right, the gradient. The gradient gives us the normal vector that we use to write the equation of the tangent plane, as well as the direction vector for the normal line. So let's go ahead, let's first define a function f of x, y, z, and we'll let it be x squared minus 10xyz plus y squared minus 12z squared. So then the gradient of f is going to be, look at this relaxing little polynomial, 2x minus 10yz, negative 10xz plus 2y, negative 10xy minus 24z. Then some of them had issues plugging in negative 1, negative 1, negative 1. I don't know. You get negative 12, negative 12, 14. If they left it like that, that's fine. I did not deduct, but it's best to use, yes, 6, 6, negative 7, okay? It's appropriate to scale down. Why? Because we're finding equations here. Okay, so for the tangent plane, at the very least, it did need to be in standard form at the very end, meaning ax plus by plus cz equals the constant. So I have 6 times x plus 1 plus 6 times y plus 1. Oh, did you forget the point was negative 1, negative 1, negative 1. Minus 7 times z plus 1 is 0. So this simplifies to 6x plus 6y minus 7z is negative 5. So that's done. And then normal line. Here we go, coming in with the normal line. Parametric equations, vector equation, symmetric equations. I saw it all. I didn't specify, so I didn't care. 6t minus 1, y is 6t minus 1. And then z is negative 7t minus 1. Again, if they did not scale the vector down and they had a different set, that was fine as well. Okay? Very good. Next problem, find the local max and min values and saddle points of the function. You must give your answer in the form of an organized table following the methods of this class. So we have to apply the D test when finding local extrema. So I need to first collect all of the critical points for my function. So that happens when both partial derivatives with respect to x and y equal 0. So partial with respect to x is 2y sine x. I'm going to set that equal to 0. Okay, so this is true. Just use your zero product property. Either y is 0 or sine of x is 0. So either y is 0 or sine of x is 0. If sine of x is 0, there's infinitely many solutions. That's why they took mercy on our poor souls and said, oh, x is only between -1 and 7. So then we only give the solutions x is 0, pi, or 2 pi. Okay, partial with respect to y is 2y minus 2 cosine x. So I'm going to set that equal to 0, which means y is equal to cosine x. So in the first scenario, if y is 0, and I substitute that in here, then I get 0 is cosine x. So then x would be pi over 2 or 3 pi over 2. Those are the only two values that fall between -1 and 7. So you have as critical points pi over 2, 0, and then 3 pi over 2, 0. Okay, cool. Next, to get the y values that go with these x coordinates, I have to go back again here to y equals cosine x. So we would have y equals cosine of 0. That's going to be 1. So we've got 0, 1 is a critical point. Y equals cosine of pi. That's -1. So we've got pi -1. And then y equals cosine 2 pi, that's 1. So 2 pi and 1. So these are your only critical points. 1, 2, 3, 4, 5. If you had any more, it's wrong. It's wrong. Okay. Then we need our second order partials. So fxx is 2y cosine x. fyy is 2. And fxy is 2 sine x. So I said they need to give their answer as an organized table following the methods of this class. So they're going to list the critical points, second partial with respect to x, second partial with respect to y, the mixed, the sign of D, classify what kind of extrema we have, if it's a min, a max, a saddle, and then give the actual function value. Okay, so here you go. I'll fill her in for you. For the most part, the issue came in this problem with solving the system and getting the correct critical points. It wasn't so much with the rest of it. Okay, so 0, 1, pi -1, 2 pi 1, pi over 2, 0. Obviously the table could be in the critical points could be in whatever order, so don't worry about that. 2, 2, 2, 0, 0. This was my favorite column. 2, 2, 2, 2, 2, 0, 0, 0, 2, -2. So plus, 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 minus, minus. If it's a minus, it's a saddle. And then the rest are local mins. Local min. Local min. Okay, and then the problem did say find the local maximum values, meaning we need the z value. And then the saddle point, just the xy is fine. If they didn't give the function value there, that's okay. These are -1s. If they left off the rest, that's okay, but they are zeros. Okay? Good. Next problem. They're doing great. This is the one I'm currently grading. I'm not quite done yet. So find the absolute extrema of f on the set D using the methods of 14(7). So no Lagrange multipliers. And then D is the closed triangular region with the vertices 3, 0, 0, 3, 0, -3. So let's draw a picture, shall we? Here's 3, 0. Here's 0, 3. And here is 0, -3. This bounds, these three lines bound our region D. So D is inside this triangle. Okay, and then let me figure out what are the equations of each of these three boundary lines. This one right here is x equals 0. This is y equals 3 minus x. Very good. And this is y equals x minus 3. So we need to first find critical points that are on the interior. So that comes from the same way we always collect critical points. So you take both your partials with respect to x and y. You're going to set them equal to 0 and then see when they're both equal to 0. So that happens if x is 1 and if y is 0. And then just always make sure, is that critical point inside the region D? Yeah, 1, 0. I didn't really label, I was being lazy, but 1, 0 is right here. That's fine, we're good to go. That's in the region. Some of them you gotta throw out. Okay, boundaries. I have 3 boundaries to check. So let's start with x equals 0. I'm gonna evaluate my function when x is 0. So at 0y, it turns into y squared. Ooh, fun. Then you take the derivative, set it equal to 0, and you get y is 0. So the new critical point that I have is y is 0, and that came from x being 0. Is 0, 0 on the boundary right here? It sure is. It's right there. Perfect. Okay, you get to stay. You're staying 0, 0. Okay, next we're going to check on y equals 3 minus x. So same thing, f of x, 3 minus x. It's x squared plus 3 minus x squared minus 2x. You can multiply it out or just do the chain rule. So 2x minus 2 times 3 minus x minus 2x, which gives us 4x minus 8. Set that to 0. I get x is 2. X is 2. Put that in the boundary equation. Y has to be 1. And is that in an appropriate place on our region or on the boundary line? So 3 minus x, 2, 1 is right here. Oh, perfect. Okay, you get to stay too. And then lastly, you have y equals x minus 3. So same process, you figure out f of x, x minus 3. It's x squared plus x minus 3 squared minus 2x. F prime ends up being 4x minus 8. You set it to 0. And you're going to get x is 2, so the point is 2, negative 1. And sure enough, yeah, that's right there. So they all stay. They all stay. The third and last place where you get critical points are on the corners, where the boundary equations meet. So 1, 2, 3 of them. We have 0, negative 3, 0, 3, and 3, 0. So altogether, there should be 1, 2, 3, 4, 5, 6, 7 critical points, and we're going to evaluate the function at all of them. So f of 1, 0 is negative 1. F of 0, 0 is 0. F of 2, 1 is 1. F of 2, negative 1 is 1. F of 0, negative 3 is 9. F of 0, 3 is 9. And f of 3, 0 is 3. So our absolute max is 9, and it occurs at 0 plus or minus 3. And then the absolute min is negative 1, and it occurs at 1, 0. Good? Perfect. Okay. Next, nice little Lagrange problem. Find the extreme values of f subject to both constraints. Oh yeah. So, let me move my paperwork. F of x, y, z equals x plus y plus z. I will call this, who should we call it? G. And this is h. Okay? Very good. So, starting off, we'll do gradient of f equals lambda times the gradient of g plus mu times the gradient of h. Gradient of f is 1, 1, 1. There you have it. Equals lambda times gradient of g is 2x, 0, 2z plus mu times 1, 1, 0. We have 5 unknowns, so we need 5 equations. Okay, first one is going to be coming from setting all of the first coefficients equal to each other. So we have 1 equals 2 lambda x plus mu. Equation 2 is that 1 equals mu. Ooh. 3 is that 1 equals 2 lambda z. And then equations 4 and 5 are the constraint. X squared plus z squared equals 2. And 5 is x plus y equals 1. Okay, I got this gorgeous freebie that mu is 1. So let's sub that back in here into the first equation because there's no other equation that has mu. So 1 equals 2 lambda x plus 1. All right, that means subtracting 1, lambda x equals 0. Either, based on our zero product property, lambda is 0 or x is 0. Now, lambda can't be 0. This is a contradiction. You can use that symbol for contradiction in equation 3. Because look at equation 3. It would say 1 equals 2 times 0 times z, and 1 does not equal 0. So you go, oh, this can't happen. This is Garbaggio. Therefore, I know x has to be 0. Okay, great. If x is 0, where do I go with that negative info? To 4 and 5. That's where you go. So if x is 0, then I know, very good, x squared or 0 squared plus z squared is 2. So z equals plus or minus rad 2. And that's from equation 4. From equation 5, 0 plus y is 1. So y is 1. So that's it. Boom, boom. That means I'm going to have 2 points, right? You basically have 0, 1, rad 2, and 0, 1, negative rad 2. Let's evaluate the function at both of these. Do you remember what the function was? It wasn't wild. It was just x plus y plus z. Yep. So 1 plus rad 2 and 1 minus rad 2. So this is our absolute max. And this is our absolute min. You know, I messed up. The whole reason I was like befuddled, I didn't mean to put this problem on the test. I meant to put the other homework problem on that was harder. I'm really mad right now. I screwed up and I gave them the easy one. They better have done well. Okay. Last one. Find the point on the curve of intersection of the paraboloid in the plane that is closest to the origin. So closest to the origin means we're trying to minimize distance. I'm going to minimize the distance squared because it'll be easier. Distance from some arbitrary point, right, to the origin, 0, 0, 0. So that would be x minus 0 squared plus y minus 0 squared plus z minus 0 squared. And you could start off doing this with 2 constraints, right? Same method as before with Lagrange multipliers. You'd have a lambda and a mu. But I've done this problem before. If you notice, you can eliminate a variable if you actually find the curve of intersection, and that will reduce the number of variables in the problem and simplify things significantly. So let's do that. The actual curve of intersection, if I just solve for 2z here, 2z equals y minus x, right? And then sub it in here, it's x squared plus y squared plus y minus x equals 4. So I will use this as my one and only constraint. And then notice it only involves x and y. So then I can just minimize the distance, not worrying about the z coordinate. So we're just going to let f of xy be x squared plus y squared. That's what I want to minimize. Subject to, oh, that means such that. We can't write that. Subject to, boom, it's on the curve of intersection. And then everything just plays out the same way. So gradient of f equals lambda gradient of g. So that'll be 2x, 2y equals lambda times gradient of g. Look right here, look right here. It's so cute. 2x minus 1, 2y plus 1. So we only have 3 unknowns. Isn't that nice? So then you only need 3 equations to solve. Perfect. So equation 1, 2x equals lambda times 2x minus 1. Equation 2, 2y equals lambda times 2y plus 1. And then 3 is just the constraint equation. Where'd you go? X squared plus y minus x is 4. So I think the cleanest way to solve this is just isolate lambda in equations 1 and 2. So it's 2x over 2x minus 1. And then from the second equation, it's 2y over 2y plus 1. I can set those equal to each other. So 2x over 2x minus 1 equals 2y over, that's right, 2y plus 1. Cross multiply and we get 4xy plus 2x equals 4xy minus 2y. These terms cancel out, and then that means x is negative y. So if I sub that into 3, I have negative y, parentheses squared, plus y equals 4. So what does that give me? 2y squared plus 2y minus 4 is 0. So y squared plus y minus 2 is 0. So I get y plus 2y minus 1 is 0. So y is either negative 2 or 1. So let's see, x is the opposite of y. So x could be positive 2, y is negative 2, or x is negative 1, and y is 1. And then I got to figure out what z is. But don't forget here, don't forget 2z equals y minus x. So that means z equals 1/2 y minus x. So negative 2 minus 2, that's negative 4, divided by 2, negative 2. And then same thing, that would be a positive 1. So Lagrange multipliers will give you both the absolute max and the absolute min. In this case, you just have to think, okay, which of these is closest to the origin? Well, obviously the one with smaller coordinates, right? Negative 1, 1, 1. So that is the point that's on the curve of intersection that's closest to the origin. 0, 0, 0. Okay, fun. Last problem. I did put an extra credit on there. Yes, I did. Extra credit's always all or nothing. So, let me just double check. Yeah. A circular plate with center at the origin is being heated. The temperature of the plate is given by the function t of xy. On the circle centered at the origin with radius pi, in what direction is the temperature increasing fastest? So it's always in the direction of the gradient. Very good. But I did not give you a particular point to plug in. That's what makes this tricky. Now, some people mistakenly plugged in the origin, but no. What are the directions saying? They said actually on the circle. So the origin is not actually on the circle. Any point on the circle, I want to know in what direction is the temperature increasing the fastest. If I look at any point on this circle with radius pi. Or radius, yes, rad pi. Okay, so there's your rad pi. There's your circle centered at the origin. And I want to know for any point that's on this circle, in which direction is the temperature increasing the fastest? Okay, so first let's compute the gradient. That'll get the ball rolling. So the gradient of t is going to be negative 2x sine of x squared plus y squared minus 3x squared e to the negative x squared minus 1. And then that's the partial with respect to x. And then partial with respect to y, let me scoot that down, is negative 2y sine of x squared plus y squared. Okay. Now, any point that lies on this circle satisfies the equation of the circle. And if it's centered at the origin and it has radius rad pi, the equation of the circle is x squared plus y squared equals pi. So any point on this circle, any xy, will satisfy this relationship. That means I can come through and replace x squared plus y squared with pi. And in both cases, I have sine of pi. Sine of pi is 0. So on the circle, what does the gradient simplify to? the gradient simplifies to negative 3x squared e to the negative x squared minus 1, and womp womp, a 0 in the y. That's fine. This is giving me the direction that the problem is asking for, where the temperature is increasing the fastest. And hopefully you notice, look at the x component. It is always less than 0. So you're not going to give one value for your answer. This is the answer because we have infinitely many points that are on this circle. But to sum up, it's always pointing in the negative x direction. Okay. And then depending on the x coordinate, it will change. It will change in length, but same direction. Negative number, comma, 0. All right, that's it. I haven't graded that one yet, so I don't know if anyone got it right. That concludes the video. I just went fast and furious and solved it. So like I said, if you want more in-depth explanation, strategy, breakdown, then check out the video lectures that are in the description and stay tuned for more Calc 3 content. My class has been putting in requests this semester, so it's been fun making more videos for them as they need it. And this last test looked a lot better than the first one, so hopefully that was one of the factors that made a difference. Plus, I can tell they're working really hard now, so that's great. Okay, don't forget to give the video a thumbs up. Leave an emoji in the comments because I like to see them. Tell me which problem on the exam was your favorite. And follow me on Instagram and TikTok, Math with Professor V.